So in this video, we're going to revisit and expand upon standing waves. Specifically in this tutorial, we're going to look at standing waves created when you pluck a string that's fixed between 2 points. Think of a guitar, a piano, violin, harp, etc. So the goal is to understand for a given shape of a standing wave, the various harmonics as we call them, we understand the relationship between the speed of the wave as it propagates back and forth, the frequency of the sound that's heard, and of course the wavelength. So this is primarily a pictorial type of tutorial. You can see right in front of your note sheet you have the standing waves already drawn. I'm going to explain how to analyze them. So ultimately, generally, we want to find out what frequency does this occur given a length of a string and how fast it's moving. And we already know that how fast the wave propagates along the string depends on the tension. So we'll bring that in to a certain extent. So let's do a quick little crude review of what we did in the last lesson. So imagine I have a string that is between these 2 points on a fixed, and I just somehow have something that caused it to vibrate back and forth. I could pluck it very easily, but let's just imagine it's vibrated back and forth. And as we've talked about, when you vibrate it at a particular frequency, waves propagate down, come back, and then bounce back, etc. Now, before you even know it, and my picture certainly is not illustrating this, for a bunch of frequencies that are generated, only certain ones will stand out such that at certain spots you will have constructive and destructive interference. So you might get a zone where the string vibrates quite a bit here and another zone where it vibrates quite a bit, and they're evenly spaced, and then you'll have zones between where they might not vibrate at all, okay? And so we know those are nodes and antinodes. So that's what we're basically going to do. It's a pretty straightforward process, but you got to be able to work it out on paper rather than try to just do it in your head. Okay, so let's start with some basic rules for harmonics in a fixed string. And I'm going to go down here, all right? Nodes are always at the ends. That's no matter what harmonic we're talking about, you're always going to get at the ends here and here where you have destructive interference. And knowing that helps us shape all higher harmonics, okay? Because there's a simple pattern to them. And that's this. Each successive harmonic has an additional node and also an antinode. So let's take the simplest, called the fundamental. Okay, and then everything else is just the second harmonic, third harmonic, etc. If you want to create the simplest possible standing wave, and therefore at the lowest possible frequency, it would occur such that you have the node at the ends, and between any two successive nodes there must be an antinode. So we have right there an antinode. So our standing wave will look like this. It looks like the string is just vibrating back and forth between those 2 points. What's actually happening in right here is much of the time we have partial constructive and destructive interference. So in other words, the string will go from here to here to here and then back and forth, all right, with a minimal amount of amplitude. The same over here, and then if we get closer to the ends, even though waves are passing by, they are always meeting, the reflected waves and the incoming waves are meeting completely out of phase, so they'll always destructively interfere and give you no amplitude. And then, of course, in the middle, you can start here at the antinode, and then a quarter of a cycle later, it'll be at the rest position. Then a quarter cycle later, it'll be at the other extreme, and then it'll just go back and forth, as I mentioned earlier. So what can we analyze about that? Well, what do we know about the situation? First and foremost, the length of the string L. That's a key parameter. Secondly, we have some idea of the velocity, which depends on the tension. But let's just say for now, the velocity of the wave as it propagates back and forth is given. So how would we figure out the frequency? Well, it's still the wave equation. So don't write this down in the space right here yet, but we know that frequency is going to be equal to velocity over wavelength. That always holds. So the goal is to translate the wavelength into the length of the string. In other words, what's the connection between the wavelength of the wave and the length of the string? And the length of the string is fixed, so that's not going to change. Well, we simply count how many wavelengths fit within the string based on the shape of the standing wave. So if we look carefully at this one, as it goes back and forth between this extreme and this extreme, how many wavelengths are represented there? Well, think to yourself for a second. Should be pretty clear, but sometimes it takes a little practice. So hopefully you came up with, and you should write this down next to it, that the length of the string, right, that's a given, equals a half a wavelength. Because we're just going from essentially a trough to a trough. We don't have two crests there, therefore we don't have a full wave. So what do we do with that? Well, then I just turn this equation around. I say then lambda must be twice the length of the string. So if the string is 1 meter long, the wavelength of the standing wave that's being created is 2 meters. So now that we know the wavelength, we can say then the frequency of the fundamental, F1 if you will, is then how fast the string or the wave is propagating through the string divided by twice the length of the string. Do yourself a favor. Do the same analysis for the second harmonic right now. Okay, I'll wait 10 seconds or so before I do it. Or you can pause. Okay, so let's take a look at this. We're going to still use this generic equation to find the frequency. In this case, we want F2 for the second harmonic. And before we do that, let's recognize how we know it's a second harmonic. Let's say we were to give you this shape without all the others with it. How would you know it's a second harmonic? Well, easy way to do it is count the antinodes or count the nodes. They're slightly different numbers, but they all, or both those views correspond to the second harmonic. So we must start with nodes at the ends. And to distinguish this from this, I have to add another node. And we have to add another node halfway between the two previous nodes. And therefore, between the nodes, there must be antinodes. And so we have a standing wave that oscillates between this extreme and this extreme. So please don't say that there are 1, 2, 3, 4 antinodes. No, at any given instant, there are only 2. And then even at a special instance, there's nothing going on. You can have the string, if you take a snapshot at the right time, look like as if there's no energy in it at all, even though there are waves there interfering. So the second harmonic corresponds to 2 antinodes or 3 nodes. Anyway, how many wavelengths are there? Well, that should be pretty clear that that's one wavelength. So I can say F equals V over lambda. That's the generic equation. And how many wavelengths are there? Well, there's one wavelength, fits with an L, so that's nothing more than V over L. Okay, because lambda equals L here. I'll write that off to the side. Here we see that L, or lambda, is 2L. And if you look carefully at the first equation and the second equation, you see that this frequency occurs at twice the value as the fundamental. Okay, not a surprise that there's a simple relationship between them. So if this occurs at 100 hertz, for example, then this must occur at 200 hertz. And you can probably take a guess for the third harmonic, which now has 1, 2, 3, 4 nodes, or 1, 2, 3 antinodes, the frequency is going to occur at 300 hertz. But to prove that, let's do our analysis. So we have 1 and then 2, excuse me, I stand corrected, 1.5. Let me trace that again for you to see. So if I start here, I've got half, 1, 1.5 wavelengths. So I'd say 3 halves of lambda is equal to L, therefore lambda is 2/3 L. So if I go over to my equation, F3 is V over 2/3 L, which is 3 halves V over L, which is 3 times this value. And then, of course, the fourth harmonic follows the same pattern. So study that carefully, come up with any questions. So let's do a problem right now to give you a little bit of practice. Let's draw the fifth harmonic. Okay, you may be asked to draw a harmonic for fixed strings, and then for the next tutorial, it could be for an open or closed pipe. But all three follow the same basic process. Start with where you know the nodes are. So we know we have to have a node here and a node here. And if I don't put any nodes there, then I'm at the fundamental. So if I want to go to the fifth harmonic, so the fundamental is also the first harmonic, so the fundamental, or the fifth harmonic, excuse me, would have to have 1, 2, 3, 4 more nodes. and I want to space those nodes out evenly. Now I have this center line here, but that's actually not going to be very helpful, so I got to break this into 4 nodes. So I'm going to guesstimate where the nodes would be. I think I want to break this into fifths. So I'm going to guess here, roughly here, roughly here, roughly there. Okay? Now between every node, I want antinodes, so I'm going to start here. I'll mark the antinodes. I'm going to mark it up here, down here. I'm going to alternate. Okay, now I just kind of connect the dots. And then that's what the wave might look like at one instant. If you want to look at the other stream, go the opposite direction. I'll use a dashed line. And there is my fifth harmonic. And a way to check, I have 1, 2, 3, 4, 5 antinodes. So what's the wavelength? Okay, now remember, this is the same situation as above. It fits within a length L. So rather than just try to reason it out and think in my head, I'm going to take my time. I'm going to say there are 1, 2, 2.5, 5 halves. There are 5 halves wavelengths there. That's equivalent to the length of the string. Therefore, lambda is 2/5 the length of the string. So I would put 2/5 L. What's the frequency? Frequency is V over lambda, and that's equivalent to V over, well, I'll do the algebra now, V over 2/5 L, which is going to be 5 halves V over L. Okay, so 5 times the original fundamental, which we should have anticipated. I also want to point out, notice that our wavelength keeps getting smaller and smaller as the frequency gets higher and higher. Okay, what would happen if more tension were put on a string? So imagine I have a guitar and I tighten the tension. If you're a musician, you know the point of that is to change the frequency. But that's not a direct change, so we want to understand the sequence of events that happens when you change the tension. So we should anticipate that changing the tension will change the speed at which the wave goes, and higher tension would be higher velocity. I think we learned that velocity is proportional to radical t. It's not equal to radical t, but it's proportional to the tension, or the square root of tension. So the velocity would increase. So why would we want to do that if I'm trying to tune a guitar or any stringed instrument? Well, when you crank up the tension, you're not changing the length of the string, you're not stretching it out, so therefore the wavelength would stay the same, okay, because L would stay the same. So if we must obey, we must satisfy this equation, V equals lambda F. If I've got a bigger V for the same L, then I get a bigger F in which the standing wave occurs, so the frequency would increase as well. And that's how you tune a stringed instrument. You change the velocity without changing the length or wavelength, and therefore your frequency will change accordingly, and then you get the sound that you want. All right, I'm going to point out one last thing. It's a nice little shortcut to all this analysis if you have a place to start or something to compare it to, is if you look at the successive harmonics. Okay, so I'm going to start from the beginning. Half a wavelength, 1 wavelength, 1.5 wavelengths, 2, 2.5, you see that each harmonic is a simple increment of the previous one. It's a half a wavelength. Okay, so if you know you have a starting harmonic, a fundamental that's occurring at, let's say, some L, then you know the next one is going to be half of it longer. Okay, we'll do more practice with that, and the next tutorial will lead into the other cases of open and closed pipes.